It's a pleasure to be in Armenia. It's the second time I'm here. The first time was more than 10 years ago. And the city is growing, and more science and tech is happening, which is great. So in this session, we will talk about this new paradigm in machine learning, which we refer to as machine learning on function spaces. It's a subject of operator learning, where the data is function rather than finite dimensional objects. And we will talk about the emergence of neural operators, which are generalization of neural networks to function spaces. Okay, neural networks are designed for finite dimensional objects, and we will talk about neural operators, which are designed for data on function spaces. We will talk about why we care about this subject and why we introduced this paradigm in machine learning. And in case you guys are interested, we can converse a lot after this session. And also, if you have questions throughout the session, feel free to ask. Before we get to the machine learning on function spaces and operator learning, let's see what we have been doing in neural networks for many, many decades. In neural networks, in the area of neural networks, we have been dealing with data where data was finite dimensional objects. For example, in images, the data is like 64 by 64 image, or in Atari games, you have 84 by 84 image. In language models, we have a sequence of discrete objects, and these are basically the settings or the data type that we have been dealing with in machine learning for almost more than half a century. Okay, and for all of these things, all of these domains, what we cared about was learning a function, which we represented using a neural network. And the whole aim was, hey, given a data set of input and output, which are the finite dimensional object as an input and finite dimensional object as an output, how we can learn a function which learns a map from the input to output. So that has been the paradigm of machine learning for a long time, and we have seen great success in speech, in language, in computer vision, and many, many domains, as you all are aware of it. Okay? But let's go and take a look at one of the universities in your neighborhood. I just picked a university in my neighborhood, Stanford University. I looked at the departments there. There are many, many departments outside of computer science or electrical engineering department that are working on data of different types. Okay? Dermatology department is working on skin and understanding of what is happening in the thickness of the skin. Mechanical engineering department is working on aerodynamics of planes, cars. We have physics department is caring about like the physics equations. We have molecular dynamics and biochemistry department, biology department or chemistry department that care about like protein engineering. We have heard in the first talk of today, or molecular dynamics. All these domains, all of these disciplines in the school, let's say in the undergrad programs, they are dealing with problems that the data is a different type. And the data in all of these domains is function. None of these domains are working on a data that is finite dimensional object. Okay? All of these domains are working on a domain that the data is function, and project this to industry. Almost all industry, except few sectors of industry, are working on the data where the data is function. From Aramco to Volkswagen to Formula One to Apple to NASA, all of these organizations and companies are working on a setting where the data is function. Okay, so they are not that much interested in like the image classifier that you have can classify image of cat or dog. They care about something which is like physics-based functions. Okay. To just give you some ideas, let's go over the problem of weather forecast. In weather forecast, I care about the weather tomorrow. Okay? The weather tomorrow is a temperature, precipitation, wind velocity, and all sorts of physical variables which are not 64 by 64 images. These are functions defined on a sphere, for which I care about spatial and temporal derivatives of it, because these should follow the laws of thermodynamics and laws of fluid dynamics. Okay? So in weather forecast, the data is function, and I care about predicting something which has a functional form. So tomorrow's temperature, tomorrow's wind velocity, tomorrow's like precipitation. All of these things I care about, and all of these problems are data is function. And what I care about is finding an operator which takes the input function, which is the state of the Earth today, temperature, wind velocity, all these variables, which are representing the state of the Earth today, and I want to use them to predict the state of the Earth atmosphere tomorrow, which is another function in a sphere. So input is a function on the sphere, output is a function on the sphere. I'm interested in learning an operator which maps between these two things. And for this output and input functions, I care about their spatial and temporal derivatives and also integration over them. Wind velocity squared integration gives me energy. I care about the energy. Similarly, in geophysics or seismology, the Earth is represented with a velocity field, which describes how fast a wave travels in subsurface Earth. And the question is, if I have an earthquake somewhere, and this is a velocity structure of subsurface Earth, how this wave propagates and what type of earthquake I'm going to have on the surface. Okay? So this is the problem is like the input is a function defined in 3D, which is a velocity structure of the Earth. The output is a function defined in 3D and time, which is how the wave is propagating in this 3D space. Okay, so the input is a function, the velocity structure of the Earth. Output is the wave solution, which is a spatial temporal function. So what we care about is learning an operator which maps input to the output. Also, as you can imagine, if I show you what happens on the surface, you can solve an inverse problem and see what happens in subsurface. What was this? If you see an earthquake on the surface, you can ask, what was the subsurface structure, which is an inverse problem. So many other problems. I'm not going to go over all of them. In ultrasound imaging, in fusion, in material science, all of this material deformation, all of these problems, you represent your input is a function, the boundary condition, or like some coefficient functions, and the output is a solution function, which is most of the time is like a function in space and time. Okay. Similarly, in protein engineering and molecular dynamics that we have been talking earlier today, and robotics, all of these problems, when I have a robot, the movement of a robot is not a time series. It's actually continuous function in time, which follows the laws of this guy. His name is Isaac Newton from centuries ago. So this thing follows that law. So it's a continuous function in time. For molecular dynamics, I have Schrödinger equation. Again, the problem is not a time series, it's a continuous function in time. So all of these problems, the data is a functional nature.
Can I ask you a question?
Go ahead.
In weather prediction task, when we have to predict tomorrow weather and the data is temperature, why the input data is function, isn't it simple regression problem?
It is so the question is like in weather forecast, the data is given to me, let's say temperature is given to me at some points on the sphere, okay, and I'm outputting the function. So the input is a function which I have access to on some discretization, okay? So I can give you a pair of data of input temperature and output temperature. Input temperature is given to you as the input temperature function is given to you as some discretization, okay? And output also given to you as some discretization, right? And you can turn this problem to a simple regression on function spaces where you learn an operator. But the thing is, tomorrow, or next second, I can give you different data point which has different discretization, okay? So what you need to do is you need to have a model which is discretization agnostic. That's what the operator have to satisfy. So you need to be able to deal with any sort of discretization that is given to you.
I don't understand the difference between simple data and when data is function.
So let's say you have a sphere, okay? Like let's say for weather forecast, I give you the temperature in Yerevan, I give you temperature in Dilijan we talked about yesterday, and many other towns around, okay? And like San Francisco, Berlin, many towns. And tomorrow I give you the temperature in different places, okay? So you need to be agnostic to way the things is discretized. The function is discretized. Temperature is a function field on a sphere, right? That we agree.
The countries are fixed in that case?
No, tomorrow I can give you a different grid. I can give you the temperature. Let's say 40 years ago, I had few towns that the temperature. Now I have like 10 billion more stations I have sensors on. Or like sometimes the sensors are balloons, they're changing their location. So this function temperature, that is defined on, is a temperature as a function on a sphere, you happen to have different discretization of it as an input. Okay.
Thanks.
Sure. That was a great question. For all of these things, this one also another setting. This function, you see you might be the blurriness of here. At each data sample, the grid discretization changes. So you're given the input function at different discretization. So that's very important to be agnostic to the discretization. So in aerodynamics and everything, all of these problems, the data is function. I don't go over all the other disciplines. Almost all the science is about data that is function. There are many others. Okay, not all of it. The majority of science is about the physics problems that are there. The data is function. Okay? So let's talk about machine learning on function spaces. So now to answer your question more in depth. In the machine learning on function spaces, the input is a function, output is a function, and I'm interested in learning an operator which maps the input function to output function. Okay? In practice, neither input function nor output function are given to me in an abstract functional way. They are given to me at some discretization. Okay? So let's say this is the left-hand side is my input, and the right-hand side is the output function. I can be given these two at this discretization. Next data point might have this discretization. It can be totally different discretization, meaning that the function is given to me at different resolution. I can have totally irregular gridding, which happens a lot in practice. So these are like the thing. My data input and output is given to me at arbitrary, at least a priori unknown discretization to me. Okay, so I need to have a model which is able to handle these types of weird discretization and be agnostic to the discretization. That's why we need an operator. Of course, in practice, I don't have this cute discretization. In practice, the gridding of the function is very, very complex, and I'm not going to get into detail, but just know that in practice, the discretization that we are given is very, very complex. Okay? So the input is a function that is given to us at some arbitrary discretization, and we should be agnostic to it. And we need to output a function. The output of the model is a function that we should be able to query at any point. And also, we should be able to compute the spatial temporal derivatives of it, because most of the time, the function we output should satisfy some laws of physics. And we should be able to compute integration over it, because of like so many quantities in physics are integration based. I need to have an integration to compute energy. I need to compute integration of the pressure on the surface of the car to compute the drag. So many quantities, we need to compute the integration. So we need to have access to the function as an output.
If you mean output is a function, it's not function in formula. It's means any.
Yes. So the question is the output. When I say output is a function, is not in an explicit formula. Is a thing that you can query at any point.
But input is a real function, right?
The input is a function which I have access to it at some discretization.
Okay.
Yeah. So like here, this input function, I have access to it at just these dot points. Let's say I give you the temperature on the wall of this room. I ask you what is the temperature inside the room. The wall, I have some configuration of sensors. I can tell you what is the temperature on this wall. And given that, which is a function on this wall and this 2D, that 2D, that 2D, that 2D domain. And the question is, what is the temperature inside the room, which is a 3D function. Okay? And yeah, so this input is given to me at some big, I don't have sensors everywhere. I have sensors in arbitrary places. We go to the next room, I get sensors in different places. And inside the room also, I have some sensor here, 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 or I have a like drone is moving around and have different sensors. So the input and outputs are functions in nature, which happen that we have access to them at some discretization. Okay, so we need to deal with these problems as functional problems, and we care about learning the operator. For neural networks, we were learning a function which was mapping a finite dimensional object to the finite dimensional object. Here we care about an operator which maps an infinite dimensional object, which is a function, to an infinite dimensional object, which is a function. And we care about that. And that's the whole field of operator learning, and this is a paradigm of machine learning on function spaces. How we do machine learning, or how we invent the foundation of machine learning when the data is function. So we know what neural networks are. Now we want to talk about neural operators. Neural operators are generalization of neural networks to operator learning where the data is function. So in neural network, If I have an image classifier like a model, if the input is 64 by 64, if I change the resolution of the input, the model does not apply anymore. Okay, because the model was mapping from finite to finite. So if I change the discretization of the input image to something else, the model doesn't apply. For neural operators, which are generalization of neural networks to neural networks to function spaces, I can represent the input at any discretization I want, or at any discretization the data is presented, and I should be able to generalize between the discretization. Okay? And another thing that's very important is I want to have this neural operator, basically neural operator, have this property that as I increase the resolution, meaning that as I make the mesh finer and finer, meaning that I provide a more detailed input function, let's say for temperature on Earth, I keep adding more sensors. Governments plant many more sensors in many places. As I increase the number of sensors, I would get more, like I need to converge to a unique operator. That's a very important thing that we want. And you also know, okay, we will get to the next slide, that we see that we actually have been doing this stuff from like some of us from high school or undergrad, that this type of things were things that we have been doing a lot. Okay, so let's see how we build a neural operator. To build a neural operator, let's remember recall how we build a neural network. In neural network, the input is a vector, is a finite dimensional vector. What we do, first layer, we apply a linear matrix vector product on it. We call it a new vector, and then we apply nonlinearity, and we repeat this. Right? That's the way we do, in a simplest way, we do neural networks. Okay, then in the conceptual way. What is neural operator? The input is a function A. Okay, and instead of having for the linear operation part, we do linear operation in functional space, which is basically kernel integration. Okay, so here I take an input X, multiply by A, matrix A, and it gives me another vector. I have a bias and residual connection. For neural operator, given function A, I do kernel integration. Okay, gives me another function, and then after coming up with the output function, I put a nonlinearity, a pointwise nonlinearity, and repeat it. Okay, that's basically what is a neural operator. This architecture is discretization agnostic, meaning that as I increase the discretization, it gets finer and finer. And it's discretization convergent, meaning that it converges to a unique operator. And also, this architecture is universal approximator of any operator. Okay, so this architecture is like similar to neural networks have this universal approximation theoretical guarantees that they can approximate any function. This architecture I'm talking about can approximate any operator. Okay, so here for neural network, the learnable parameters were this matrices that you will multiply by the input vector. In neural operators, this kernel is a learnable parameters that you can learn. Okay. Any questions so far?
How do you represent these things?
Come again?
How do you represent this kernel, for example?
A kernel, simplest way, this kernel as an input receives x and y, which are the coordinates of the domain. This one, the simplest way is to just represent it using a neural network.
I see.
Okay, it's just the simplest way is
then you learn the weights of that.
to learn the weights of that neural network. Then later you do the integration over it. Okay, or one another thing. This is like if I replace this x and y to x minus y, this becomes convolution, right? I can do this thing in Fourier space, okay, and then I can learn the Fourier coefficients of the kernel and do multiplication there. Okay, there are many ways to do that. You can represent this k as wavelets. You can do plenty of stuff.
With respect to the agnosticism to discretization, you showed before how you make your input somewhat like variant to discretization, but are there also ways to do it with your neural operator? Like for example, in Fourier base, you just increase the spatial frequencies, or in case of the image.
Say it one more time.
Are there ways to make it discretization agnostic via your actual network?
Yes. So let's look at this one. Just look at how we make it discretization agnostic using this framework. So here I have this integration, right? which is integration of this learnable function with respect to A. As I said, the function A is not given to me as an explicit way, it's given to me as some discretization. And we all know that we cannot compute the integration using Riemann sum. We learned in high school or undergrad. So basically, I can compute this integration or approximate this integration that I have here by this Riemann sum integration. Okay? Which I multiply by delta xi, which was the volume. You remember that they had this rectangle thing, and at any discretization you give me, I can approximate that integration. So that's the way you compute this integration. And as you make the resolution finer and finer, this integration becomes more accurate and more accurate. This is basically what you do, and the way you implement it is basically similar to this. It's like in computer you construct a graph, and when you do integration, you just integrate over all the points around it. So that's basically the way you compute this. If you want to compute this using Fourier methods, I will get in next slide. We'll get there. Any other question?
Your system is learning. Using back propagation, but where is your target?
So the input is this one. Okay, this is the input function that is given to me at some discretization. I compute all these layers, and the output is. So this is my output. So the output is another data point. Let's say today temperature is the input. Tomorrow temperature is output.
You can compare output with any target.
Yeah, it's a supervised learning problem. You take your model outputs a function. You query at the exact same points that you have the data on, and compute the L2 loss on it. But the L2 loss should be on function spaces again.
It's not supervising learning.
It is supervised learning. The input, I have input, which is a function. Output is a function, okay, which I am given both of them at some discretization.
Your system is learning to.
My system learns to map this input function to this output function, okay? And pairs of data I have is pairs of input and output.
Okay, you have output.
Yeah. So like I have today's temperature. For last 40 years, I have today the temperature at time t and temperature at tomorrow. I have it for 40 years, let's say. Okay. Yeah. Good questions.
Are there operators similar to variational autoencoders?
Say it again.
Are there operators similar to variational autoencoders when we have a distribution function and we sample from it?
Great question. So let me answer this question this way. The field of machine learning function spaces is like a total a field by itself. So anything we have developed in finite dimensional object setting, we need to do it for function spaces. VAEs, we have done it for finite dimensional objects. Okay, now we need to do it for function spaces. And there are papers. It's called variational autoencoding neural operator. There's a paper named that, and there was another paper came out like a few weeks ago on this. So people actually have developed VAE type generalization of finite dimensional objects, finite dimensional domains to functional domains. So there are works. So VAEs are subsection, like there are type of problems or a framework for finite dimensional objects. We need to extend it into function spaces. People have done it. I can give you other examples. GANs, people have developed them for finite dimensional objects. You need to develop them now for functional spaces, because generative models in function spaces is important. That tomorrow's temperature is not a deterministic thing. It's a stochastic thing. Or diffusion models, people have developed them for finite dimensional domains. You need to now develop them for function space domain. Active learning, people develop them for finite dimensional domains. Now we need to do it for function spaces. Similar like uncertainty quantification, Bayesian frameworks, anything in machine learning we have developed for finite dimensional objects. Now is the time to develop them exact same thing, generalize them for function spaces.
When using diffusion models for 3D object generation, is that infinite?
So it depends on the problem setup that you have. If you are dealing with problem of 3D object as a function, yes. Okay, and that's what probably you should be doing. Like 3D object is a function. Let's say the surface of the car is not a point cloud; it's a function. Okay, point cloud can be anything. It's a continuous function. So you need to deal with it as a function. Of course, I'm not saying do it now. The things this field needs to be developed further. Okay, but this is a paradigm that we're pushing at the moment to treat the data, if the data is function, treat it as is.
That question, right? Because we control the linear integral and non-linearity, we cannot have a state when we have an improper integral, yes, because nature is more complex. It's just an approximation. So
Say one more time.
So we are coming up with linear integral and non-linear function. Right? We cannot have improper integral there, right?
We can. Like the thing is, this is the simplest way. This here, if you look at it, I just showed in this slide. I literally just showed how you take MLP and generalize it to function spaces. Okay. I'm not showing many other complex settings. There are how you generalize CNN to function spaces, how you generalize like long range receptive field CNN to, how you generalize unit to, how you generalize transformer to operator learning. So I'm just showing the simplest case. Anything else you have in mind, definitely we should do it. Like this is not the only way. It's just an example how we go from MLP to function spaces, to neural operators. But there are gazillions of other architectures that are already developed and they need to be developed, and you can have improper integration as long as you can have a consistent architecture. Consistency means you need to make sure that your architecture does not behave weirdly, in the sense that as I increase the discretization, as I make the discretization finer and finer, your operator should not go to garbage, okay? So if I apply GNNs on the point cloud setting, as I increase the discretization, so in GNN, each point is connected to neighbors, right? So as I increase the discretization, each point is connected to neighbors collapse to itself, and you get a point-wise operator. So GNN is not a fully proper architecture to be used for function spaces. That's why we have this thing this is called graph neural operators, the graph-based neural operators, or kernel neural operator. They learn this kernel using neural networks, but the whole integration is happening as an integration. This one is like literally the Green's function integration we have been doing in wave equation, signal processing. If you have background in EE or CS, you probably have seen something like that in the past. Yeah, good question.
How smooth does your real-world data have to be? If you assume it's a function, I guess in reality, often the data you get is maybe not quite a function.
Okay, great question. So the question is, how smooth you need to assume the data in real world is, and that's the thing. So for each, that's a great point, and that's one of the things I want to bring up here. So in machine learning, we have been working in a domain of computer vision for a long time, and we developed so much theory, foundation, and architecture in that domain. We also worked on a language. We developed theory, framework, losses, metrics, you name it, so many things. When we go to science is not one domain. If I'm working on aerodynamics of cars, that's one domain. If I'm working on like seismology, that's a different domain. If I'm working on, I don't know, like reservoir engineering, is totally different. For each of these domains, I get different problems. I need to design different architectures. We did not apply units, which was defined for image segmentation type problems, to NLP problems. Okay, so we need to design a specific architecture for each of these domains. And there are domains in subsurface engineering that the output is actually discontinuous. And for that, we have different types of architecture to be designed. So we develop different, by VMing, the whole community has been developing different architectures suitable for a specific problem. Let me show you this problem of Navier-Stokes, which is a fluid dynamics. The integration is very good to be done in Fourier domain, and that adds a lot of smoothness biases. So here I see is like very smooth, so I can actually use spectrum method to carry that integration. So basically that integration we have had, if I turn it to the convolution, which was Hrant you were mentioning, I can compute this integration in Fourier domain by taking the input function and compute its Fourier transform, and take my kernel and compute this Fourier transform, multiply in the Fourier domain, and then do the inverse Fourier, and this would give me an integration. But if you look at the closer, here I only care about the Fourier transform of my kernel, so I actually don't need to learn the kernel explicitly. I just learn the Fourier coefficients of it, and it's going to be extremely efficient. That's architecture is called FNO, Fourier neural operator. You might have heard of that, which is very, very fast. Okay, for this we are using the fact that, hey, in fluid dynamics, Fourier bases are extremely good. Okay, so this is a domain experts told us, hey, in fluid dynamics, use Fourier. Fourier is just the best. And that's why we did integration in Fourier domain. If you go to different domain, the domain experts say, hey, you probably use Laplace basis. Or you go to some physicists, they say, hey, use this basis in Hilbert space is best. So for each problem setup, we will use different ones. If I have discontinuity, I will make sure that my kernel is not just a neural network. I make it like somewhat symbolic to make sure that it has some discontinuity in it that it doesn't learn it by itself. Okay, this is basically the generalization of CNNs to neural operators. Okay, this is an example that you can train FNO on a given resolution. I think it was 64 by 64 and test it on resolution of 256 by 256. You can train on one resolution, test it on another resolution. And it's very important because most of the time we don't have access to very high resolution data. You have access to more low resolution data, so you can train on low resolution, fine tune high resolution. So it doesn't care about the discretization. It's very, very important point. Okay, so let's see what are the recent developments we have. I mean, recent like last 4 or 5 years developments we have had in the area of neural operators. We talked about the fact that in weather forecast we care about neural operators because the data is function. So here we developed a neural operator architecture for weather forecast that takes dozens of variables as an input, like the temperature, pressure, velocity and stuff, vorticity of the wind and stuff at different pressure levels of the Earth. Atmosphere is thick, and predicts every 6 hours. So given the current state of the Earth, we predict the next 6 hours. And this model was 45,000 times faster than the traditional or conventional methods. Okay, and it was more energy efficient and blah, blah, blah. So it was good. And very important thing, which also is related to the morning talk, is the fact that here we have access to 40 years of real world data. Okay? It's like we have access to real world data of last 40 years, but the operational method, the simulation that we have developed in the last 50 years, like for actual weather forecast happen on our phone, that thing, many smart people sat down to design that. I think they have like 1,400 lines of equations that they designed, that each of them has like approximation and stuff to be able to forecast the weather. And it does a great job. As you see, we have access to weather forecast. But these models, they can outperform those because we have literally trained them on real world data without having not much of human biases. Okay, so this is very important to note that is more accurate to some extent, and also what is called is very faster, like 45,000 times faster, and more energy efficient. But one thing is very important to note here is the weather is somewhat stochastic. So tomorrow's weather is not like, I cannot tell you the temperature is like in Celsius is 25. I can tell you what is the distribution of it, okay? But weather forecast models that we're using right now are quite slow, and we cannot run them many times to come up with a distribution. At most, we can run them 50 times. This one, you can run it thousands of times. And let me show you. Thousands of times to come up with the actual tracks of possible, like if hurricane is happening or tomorrow we say it's raining, we can literally say, hey, it's raining with 10% chance, it's not raining with 90% chance. So these numbers are more accurate. And some tail events, if there's a hurricane is going, let's say, we deal with hurricane in the US a lot. If there's a hurricane going and suddenly it's going to change its direction, I want to know. Like if there's a 5% chance that the hurricane was supposed to hit Alabama, suddenly goes to Florida, I need to know. Okay, even if the chance is 5%. So for this problem, we keep developing more architectures, and this is a spherical harmonic-based architecture where the integration happens using a spherical harmonic basis. There are many other companies and organizations and universities have developed more architectures upon this work, and this field is moving forward. Question?
How does it compare to GraphCast?
So that's a great question. So GraphCast the architecture is similar to this. Come on, I thought it's very much closer. So GraphCast does this integration this way with one main difference. So GraphCast treat the problem as a graph problem. Okay, change the resolution, it doesn't work. That's a problem that we have been communicating with them that, hey, this problem is not a finite dimensional problem, is a function problem. And in this area, we have one data set has the same, okay, we have many data sets. Even the data set we train has different discretization. We have Gaussian grid, we have lat long grid, we have reduced Gaussian grid. So the data is given to us at different discretization. GraphCast is a great endeavor, but the problem is like they treated this integration and stuff as integration on the space. They did it on the graph, which means that if you change the discretization, it doesn't apply. And that's the problem that's the problem that the weather agencies are, as far as I know, they are like struggling with using it. But it's a great work and outperforms the first model I showed you. Like the paper we wrote like a couple of years ago, they wrote that one 2 years ago, and it outperforms everything we have. But the problem is like we need to make sure that the model is neural operator, not neural network, because the data is given to us at different discretization. And also there are VIT-based method there, people plug and play. Great works, we should do those, but at the same time we need to know that the problem again is not a vision problem. If when you apply VIT, if I change the discretization, it doesn't apply. And any data point you touch here has different data. Even in one data set, different data points have different discretization. You cannot have VIT type method. You can generalize VITs to neural operators and use them, but you need to do that. You cannot just plug and play. Okay. So we talked about the weather forecast and the fact that we used domain knowledge to develop the architecture.
Can I ask one more question?
Where are you? Oh, okay, go ahead.
When collecting 40 years weather data, do you count all sensors changed?
Yeah, the domain experts take care of that thing. They take care of the fact that the sensors change, sensor quality has been changing. We are getting more sensors. All of them are taken care of.
And when using neural operators, we can change resolution.
Oh, 100%. Yeah, that's the whole point. Neural operators are designed that you can provide the input and output data at any discretization. Okay, good. So we talked about weather forecast. For seismology, same thing. I give you the velocity structure of the Earth. I ask you how the wave on the surface of the Earth evolves. You can train a neural operator which does that. But very important thing in seismology we need to notice is in seismology we care about this forward map which says what given the velocity what is a wave on the surface. But what we care about is actually inverse problem. We have observation on the surface. The question is what is under the surface of the Earth. So that's a very important problem. So now you have a neural operator which can tell you given the velocity what is the solution, wave solution on the surface. Now you can have a solution on the surface of the Earth and you can just do backpropagation on the input function to see what was the subsurface Earth structure such that we are receiving this surface observation.
You learn on forward data and then do backpropagation.
Yeah. Yeah. You
solve the inverse problem.
Yeah. So you have you learn this forward operator, and you have U hat, which is a U observation on the surface on a bunch of points, a bunch of stations. You just minus them L2 loss, and then optimize A such that you minimize that loss. Okay, that's very important because this whole thing is differentiable. Most of the solvers there are not differentiable and very, very expensive because these are not, you don't run them for next time. So you run it for like 10 seconds and it's like high frequency solvers.
You don't have the adversarial problem? Like
You do. Yeah, okay. That's a great point. This is the first work in this area. The whole thing, we did all this GAN inversion stuff for like 4 years from 2017 to 16 to 2021. Still people do GAN inversion for images. This is the place you care about inversion. Image inversion is important, but inverse problems are defined for these problems. Similar to uncertainty quantification, we talked yesterday. Uncertainty quantification, we do it a lot in machine learning, but uncertainty quantification are the problems that we learn that are important in science, not image classification. Okay, so all of these things we should develop. Okay. Just let's see this. See this one. Just a second, sir. So this is about injecting carbon. This is the only tool we have at the moment, like humanity has, to battle climate mitigation. So here we inject carbon dioxide in subsurface Earth, okay, to basically reduce the amount of carbon dioxide in the atmosphere. So these are these reservoirs. We inject them in subsurface Earth, and they hold the carbon dioxide for like 30 years to thousands of years. So this problem, we do it with extreme high resolution, and we use the domain understanding or domain experts' knowledge to design the architecture. This is not one of the architecture I showed earlier. It has a specific architecture. It's called nested FNO, and is specifically designed for this problem. And you can do subsurface. You can inject things in subsurface and see what happens with 700,000 times speed up. Okay? What does it mean? It means that I can see for different configuration of the wells that I had and different injection rate, how much I'm going to store carbon dioxide, how big the thing gets. Okay? And I need to do it with uncertainty quantification because I don't have access to subsurface rate, like subsurface structure exactly. I have access to subsurface structure up to some uncertainty, and I can run this for all the realization of the subsurface and come up with the solution distribution, and do the uncertainty quantification, risk management, and risk assessment in 20 seconds as opposed to 20 years that was used to take. So this is like one of the bottlenecks that you can do, and one of the reasons I'm saying that we are entering a new era of science is because now scientific discovery or scientific developments can happen in these fraction of second as opposed to years, or like you spend like 5 PhD years or PhD students years to develop something. Here you can do it in just a few seconds. Okay, now your question.
I think that graph neural networks can solve this problem similarly. What you can say about?
So graph neural network, as I said earlier, it connects each point to its nearby points, right? We have something else called graph neural operators, which came like at the same time. And in the graph neural network, you connect each point to the nearby. Now, I give you 10 of this data points, and 11 data point has 50 times higher resolution. Okay? So each point in graph neural network is connected to its neighbors, right? Now I increase the resolution. This point is connected to its literally next points. Okay? And I make the resolution even higher and higher. Take the resolution to infinity. This point is connected to itself. Okay, so the graph neural network collapses to a point-wise operator or computes the derivatives. It doesn't do the integration. That's the problem. That's the difference between doing graph neural network, which is an operation on a graph, as opposed to doing graph neural operator, which is an operation on a metric space. So in graph neural operator, I do integration in this region, no matter how many points you put there. Okay, if you remember, graph neural operator is that integration was Riemann sum integration. Green's function solution, let's say for wave equation or for Poisson equation, all of them are like you have a kernel, you integrate over domain, no matter what is the discretization. Okay, that's the difference. So graph neural networks are basically have this thing that they collapse to a pointwise operator, but graph neural operators are going to stay general and converge to a unique operator, so they are consistent. So that's the difference. You can apply it. I'm not saying, but again, you can apply neural networks here. You can take all the points and make an array and apply MLP on it. You can do it, but I'm saying that know that, hey, next data point is going to have different discretization. Sure. One of the topics that is an interest of this session is the molecular dynamics. In molecular dynamics, I have a molecule that has many atoms in it, and atoms are moving. Okay. In 3D space and time. And again, this problem is a continuous in time problem. The prior works in this area treat this problem as great prior works in this area, which are like very fascinating. Have developed many foundations there. Treat this problem as a time series problem. So you go from time step t to time step t plus 1. Okay? That's what we are doing in the area of like molecular dynamics. So I take the current time step and predict the next time step. Or I do neural MD. I compute at the current time step, compute the force or velocity and just compute the integration and go to the next time step. All is great, but this data, again, is a continuous function in time. This data is not a time series. It's a function. You have a snapshot. It looks like a time series, but if you look at closer, it's actually a continuous function in time, which you have access to it on some discretization. Okay? So if it's a continuous function in time and you have access to it at some discretization, do not treat this problem as a time series. If you apply, let's say, a transformer directly on this, transformer works for any discontinuous thing. Here, you don't have that discontinuity. And also, if you treat this problem as a function space problem, you go from, you basically predict the whole time interval instead of like next time step. So I go from this time interval and predict next time interval, okay? Now my supervision not only comes from the last time step, but also all the intermediate time steps, okay? And my solver produces all these intermediate time steps. Before I was just ignoring them, so now I'm using all these intermediate time steps. Basically, I'm using infinitely more supervision, okay? Because I'm using all this intermediate time steps to further supervise my model. The second thing is, I know that this trajectory should follow Schrödinger equation. Okay, I can compute temporal and temporal derivatives of it and put it in my Schrödinger, or go to Schrödinger's house, knock his door, finds his cat, and ask him, hey, can you check this derivatives I have? And then we can check in to see whether the thing we are emulating is correct. If I go from time set t to time set t plus 1, I can simulate the molecular dynamics, but I cannot emulate it. Emulation means I actually need to I should be able to verify the physics. So in molecular dynamics, what we say is, instead of going from time set t to time set t plus 1, use a neural operator framework and map an interval to an interval. Okay, and this way you actually get a functional view of it. And by doing that, you can just also this change doesn't change much of the architecture. It's just small changes in the architecture. And making those changes, you can outperform this all the baselines by just making this a small change of turning the problem from time series to functional data. Okay.
What is the benchmark? What are these numbers?
So these numbers are accuracy, and these are like MD17 or a bunch of other data sets that they were at the time were like a benchmark for molecular dynamics. And we took the EGNN, the set of our EGNN. EGNN is equivariant graph neural network, which treats the problem as a time series, and we turn it to equivariant neural operator in the sense that you go from the graph from the graph data to continuous in time function on a graph still. And also this work I'll share with you guys. It's not just for molecular dynamics. We have applied it for n-body problem, for joint prediction of robotics, all of these things. It's just a small change in architecture improves the performance unanimously. Okay.
So the task here is to, what is the task?
The task is like you go from time set t. The task is what is your accuracy at time t plus 1.
You know that from some ground truth.
Yeah, you have the data. You have the MD7, like you have molecular dynamics based data sets.
I see.
Yeah, you supervise train it on some part of it, and then test validate on the left out held out data. And for that setting, you just compute the error your model is making on prediction of the held out data. But it's also supervised by the temporal data. It's like temporal data. You train on this chunk and test on another chunk. Okay, so this is one setting that the data is a function. That in molecular dynamics, I also talked about the humanoid walking. I'm not showing the results here, but you can take a look at the paper. But one other thing I want to point out is this is not molecular dynamics or robotics are not the only settings that the data is functional for. Even in diffusion, in diffusion models, you go from noise, you refine the noise over time and go to the image, right? And there are many, many methods that do distillation. Go from noise and directly learn a map from noise to the image or to intermediate things to distill the map from the input to the output. Okay, instead of running the ODE solver or SD solver going from the noise to the image, we generate a data set and you train a unit to go from the noise to the image. So that's the way we do distillation of the what is called diffusion models. Here, with what we say, hey, from this noise to here, I'm going through a continuous function in time. Okay, so now, how about we give the noise as an input and output the whole continuous function in time and use intermediate points as extra supervision to train the model further. And just doing that, just take the existing distillation model and add this component, continuous temporal component to it. And what you get this method that distills distills like diffusion models, and you can improve the. I remember going from like 4.5 FID to 3-ish FID. I just don't take these numbers seriously, but I need to check the paper. But I think the improvement was like on 20-30% over FID. Similarly, there was a paper at, I think Eichler from Apple. They actually treat the biosignal. Back in the day, we were treating the biosignal as the sequential data, okay, time series data. They switched to neural operator, and they're able to deal with any sensor which receives the biosignal at any frequency. Okay, because the neural operator doesn't care about the frequency at which you are sampling. It's agnostic to frequencies, and the data set of the biosignal has many different frequencies. Yeah, so we developed further models for aerodynamics of cars, and I'm not going to the depth of it, but one of the things I'm trying to carry here in this slide and this slide is for any domain you need to design a different architecture. Here, I'm showing this plot. But each of these pixels is not a pixel. Each pixel is a domain of the PDE, and inside of it you need to solve the PDE. So you need to come up with an architecture of multi-scale for this problem. So for each problem you design a different architecture. Do not plug and play existing models to different problems. Design the thing for that problem specifically. Okay, as in conclusion, I think we all agree that AI and science together are putting their hands together, and this is going to be the future of science, and the speed up that we get and accuracy and the flexibility we will get from using AI method in science is like amazing, and we should expect many great stuff happening. And also anytime you're dealing with functions, with your data, see whether the data is function or not, and remember that neural operators are not like one architecture or two. As a framework, you need to design a neural operator of your own for the problem that you're dealing with. And yeah, so I'm very excited about the next decade or two of science and developments we're going to make. Thank you.
We have time for questions.
Does it have any relation to neural ODs?
Yeah, definitely. So actually, there are some researchers that they generalize neural ODEs to what's called for functional space setting. So in neural ODE, you have, let's say, 10-dimensional object. Okay, it moves in time, right? And you have a neural ODE which you've learned the forcing for this 10 thing to move. There is a work that showed that if the input instead of being the thing you are trying to do the ODE on is not a 10-dimensional object, is actually a function, you can train a neural operator. They design a neural operator architecture which learns the forcing on function spaces and move the function in time. Okay, for Navier-Stokes it makes sense, like you have a function in time. So again, neural ODE are not comparing, you don't compare neural ODEs with neural operators. Neural ODEs are temporal dynamics on finite dimensional objects. You can develop a neural operator type ODEs in function spaces and develop that thing. So these are like another thing that these two things are not comparable. But yeah, people have developed method that you learn to train they design a neural operator on function spaces to compute the forcing on function spaces and then move the function in time. Is a neural ODE based. I forgot what they call it, neural PDU or something. I need to take a look what they call it. But the idea is like this: you train a neural operator which compute the forcing in this 2D domain as a function. The force is a function. The force for neural ODE is like a 10-dimensional object. Here is going to be infinite dimensional object. The force is a function in a 2D field or 3D field, and you move that thing as using ODE.
You said you can't easily transfer it to another problem, but in the case where you know the analytical expression, often your function or your output function is a function of many functions. So to what degree would you recommend to like train this end to end? Or let's say you have an equation that has the first derivative and the second derivative. Would you recommend to train one neural operator for the first and another one for the second? And could you generate like a neural operator function bank for the people like us that maybe can't train it ourselves but won't use it?
Yeah, sure. So that's a good point. So the one thing I mentioned that it's very important to develop neural operator architecture for a problem at hand. But most of this I showed that we are still using similar architecture. So it's same architecture-ish. Like the FNO has been applied for weather forecast, for seismology, and all of these things. So it's still like we don't need to drastically change the architecture. It's still same architecture-ish work, but we need to advance it. But regarding finding like our neural operator architecture that are working for different derivatives, yeah, it's definitely possible. But one thing I need to note is that the fact that these things are not that computation expensive yet. Okay, so these are one of the cool thing about all of this new direction, this field is not like LLM that is extremely mature, that each run takes millions of dollars. Each run takes like half an hour of the H100. So these are like, remember what we were doing in machine learning 15 years ago? That's type of like, maybe 10 years ago, these are the type of computing we need. And also note that the foundation of machine learning is not developed here yet. So that's another thing we all need to together develop, and I think is a great opportunity for many people who don't have access to extensive like compute power to develop things here. And another thing, very important thing is anything we developed here, any paper we wrote immediately got used in industry. So the impact you have in industry is huge. It's like weather forecast stuff we did, or the aerodynamics of cars we did. They were first papers. People at the car manufacturing company, I'm not sure I can name them, but the big names are using these things. Like literally we wrote the first paper and they're using it. Important thing is, these are just first papers. We need to write many, many more works in these areas to develop and mature these fields. Yeah.
Firstly, thank you for your extremely interesting lecture.
Thank you.
And when you talked about atoms and molecular moments, which function is before operator was from space?
So in the molecule setting, you have this. This is a molecule, right? So the data in the space is on a graph. It's literally a graph. There's no function in the space, unless you go to the other domain. So here's, let's say you have 20 atoms, which are like in a graph. They are moving in continuous time like framework. So the input to the neural operator is like an interval. The output is an interval. Okay, so you take an interval of the behavior of the molecules, the molecule or atoms in the molecule, and output the whole continuous function in time behavior of the molecule.
So function before operator is function from
Time.
From one graph to.
So it's a graph in time to a graph in time. So the functional part is actually the time. The fact that the thing is, the graph is a function in time here. So the input graph. But in the spatial domain, you will still have GNN. It's graph neural network. Okay, but in temporal domain, you apply the develop neural operator specific architecture. If you have time, there's another question there.
Just as, what do you think, is it applicable for software enhancements and for trajectory prediction?
That's a great question, and answer is yes. I'm not saying we should do it. The thing is, the advancement in that direction using neural networks is very ahead. And if you want to use develop anything in this area, you need to make sure that anything you develop in the first immediate step is not going to be as performant as the mature neural network ones. Okay, but in the end, if you do that, what happens is like you can apply any constraint on the trajectory. So if you okay, let's see what people in racing cars do. They look at the trajectory. They actually make sure that the derivative in simulation, derivative of the trajectory is such that they can have at most drift without sliding. Okay, so that's very important. You can't do it using neural network approaches. You need to do this kind of things that output the full trajectory in time, that you can compute all the derivatives to see what are the outward forcing applies. So it's very important to apply, but people have not done it. So if you are interested, definitely we should talk more, and definitely this thing to be applied. So they told me to shut up.
This was a great presentation, and I think very active Q&A. So thank both Kamyar and the audience for